Hello! On this week we will talk about detectors in high-energy physics. We will view several detector designs and consider different detector systems or subdetectors. We will see how these systems work and what particle parameters they measure. We will learn how detectors recognize particle, measure their energy and momentum, and how they estimate particle types. Also, we will see several cases in high-energy physics where machine learning can be successfully applied. At the end of this week, you will know how detectors work and what systems they have and what data they produce. And we start this week from a simple particle decay. Consider a particle d0 that decays into two other particles, a pion and a kaon. In this example, d0 is also called a mother particle, and the kaon and the pion are called as daughter particles. Each of these particles has a certain energy, momentum, and mass. Energy and momentum of a particle are determined by speed of this particle. Mass of the particle is defined by its type. In this case, in this example, we have three particle types: d0, pion, and kaon. All pions have the same mass, and its value is different from kaon mass, for an example. From the energy conservation law, we know that energy of the mother particle d0 is equal to the sum of the kaon and the pion energies. And from the momentum conservation law, we know that momentum of d0 particle is equal to the vector sum of the kaon and the pion momentums. Also, we know that energy, momentum, and mass of a particle are connected by the equation shown on the slide. These equations allow to estimate mass of the mother particle d0 using masses of the daughter particles, their energy and momentum values. Also, this expression requires an angle between the kaon and the pion trajectories. However, the daughter particle trajectories are needed not only to measure the angle between them, but also to check that these particles, kaon and pion in our case, originate from the same point, from the same particle. It becomes more important when we have several decays at the same time. Detectors in high-energy physics and their different systems are needed to estimate a particle trajectory, momentum, energy, and its type to be able to recognize particle decays and reconstruct parameters of mother particles. In this example, its mass. On this week, we will talk about different systems of detectors in high-energy physics experiments. The systems, or subdetectors, are tracking system, ring imaging Cherenkov detector, electromagnetic and hadronic calorimeters, and muon chambers. Tracking system recognizes a particle trajectory or track, estimates parameters of this trajectory, and measures the particle momentum. Ringed imaging Cherenkov detector estimates a particle type using its momentum measured in the tracking system. Electromagnetic and hadron calorimeters measure particle energy, and muon chambers recognize muons and also estimate their energy. This week we will talk about how all these systems work and how they recognize particle trajectories and measure their energy and momentum values. Also, we will talk about the particle identification. The goal of the particle identification, or PID, is to identify a type of a particle associated with a track using responses from different systems. Particle types are electron, proton, muon, kaon, and pion. We will consider several machine learning approaches that help to identify a particle type with high quality. Moreover, we see how to provide independence of this quality from the particle momentum or other parameters. Consider several detector examples on Large Hadron Collider at CERN. There are 4 major experiments at CERN. These experiments are LHCP, ATLAS, ALICE and CMS. From the previous week you know that Large Hadron Collider has 2 beams of protons that fly in opposite directions. Each of these beams are divided into bunches. Each bunch has about 10 in 11 protons. Bunches of the beams cross each other inside the detectors. And there are several proton-proton collisions are generated inside the detector during the bunch crossing. The proton-proton collisions produce a lot of other particles that decay into other particles and so on. The detectors recognize these particles, estimate their types and measure their energies and momentum. Each bunch crossing with all generated particles is called an event. There are 40 million events per second are generated on Large Hadron Collider at CERN. Consider several event examples. Let's consider the LHCP detector example shown on the slide. LHCP is a single-arm forward spectrometer which registers particles flying in one direction. LHCP detects about 100 particles in an event produced by a proton-proton collision in the Large Hadron Collider. Trajectories of these particles and their responses in different detector systems are shown in the figure. Tracking system responses are shown as magenta and blue lines. Blue and orange cells represent colorimeter responses, and green cells correspond to muon chambers. Follow the link on this slide, you will find an interactive 3D model of the LHCP detector where you can look at these events. In the next video we will look closer at each of these detector systems. The second example is the ATLAS detector. It has a cylindrical shape and registers particles in all directions. Each event has about 1000 particles from a proton-proton collision in the collider. The detector provides high precision of the particles detection and it's able to recognize decays with a lot of daughter particles. Example of such decay is shown in the lower left corner of the slide. In the next video we will consider tracking system of a detector in high-energy physics. We will see how it recognizes particles' trajectories and estimates their momentum.